imagine you have some information, you have some records that have a bunch of properties, and what you want to do is to answer a question that is a yes/no question about these things. So the example I gave last week was I've got about 8,500 descriptions of types of mushroom, and what I want to know is, should I eat that mushroom? And that's quite a complicated problem, but we'll look at a simpler problem and kind of scale up to the mushroom thing from there. So imagine I want to know whether I'm going to play golf today, and I look at the outlook, and it might be rainy or sunny on particular days, and I look at the temperature. And I look at the humidity. And I look at whether it's actually raining now.
Is this a training set? Or?
Yes, this is the input data. And then, so here's my answer. Did I play golf on that day? And here we go. Now, if each of these were like Boolean things, we could build a truth table about this. So I could say, is the outlook rainy or sunny is a Boolean. Is it raining is a Boolean. Now there's an infinite number of Boolean questions I can ask about like the temperature. Is the temperature above 23.6 degrees? Is the temperature above 23.59 degrees? Is the temperature above 23.595 degrees? I'm not going to give the whole list, but you get the idea, right? Yeah. So problem one, which is a problem that we're going to skip over for the moment, is how to work out, how to derive yes/no questions from this. But let's imagine that we've discovered that the temperature being over 18 is a useful factor somehow, and so that is no, yes. And we discovered the humidity being over 75. So now I've got 1, 2, 3, 4 different Boolean properties I can ask to get my Boolean outcome. Now, basically what I can ask is the question, is this true or false? And the question, is that true or false? And the question, is that true or false? And the question, is that true or false? So I've got 4 different properties. That means 2 to the 4, which is 16 different outcomes. What I'm trying to do is to discover there is a large list of functions that, given 4 inputs, will give a yes or no answer. There are actually 2 to the 2 to the 4, which is 2 to the 16, which is roughly 66,000. And all a decision tree, a single decision tree is just one of these functions. So maybe I ask the temperature question first, then I ask the humidity question, and over here I ask the humidity question as well, for argument's sake. Then down here I might want to ask about the outlook, and over here I might want to ask about the rain, over here the rain, and over here the rain. And then obviously over here I need to ask about the rain, because that's the one remaining property, and there I need to ask about the outlook. And then each of these is a no, a yes or no answer. And there are 66,000 of those for my very simple question. Here are 4 pieces of information about the weather. Do I go and play golf? Now imagine that, that I've got kind of 23 different properties of my mushrooms that I'm trying to understand. So I've got 2 to the 2 to the 23 different pieces of information I can look at. 2 to the 24 is about 16 million, 16.5 million, so this is going to be about 2 to the 8.5 million.
Crikey.
All I need to do is to choose the right one. That is decision trees in a nutshell. Now, the problem we have, this is the one useful outcome of computer science, is what? Is that there is currently no, this thing does not grow as a polynomial. It is a non-polynomial problem, which means that as far as we're aware, there is no expression, there's no algorithm that can be written as a thing that scales with polynomial factors on the size of the input. So I can't build an algorithm that scales as like n to the 26 plus 16 n to the 14 or whatever, which basically means that there is no way to shortcut this 2.2 to the 8.5 million. What you have to do is to build all 8.5 million of your functions and test them all and see whether you see where you find the one that yields the same answers as the training set. That's quite boring. It takes a long time. So what we want to do is to find some heuristic way to prune this huge input set. Now, Joe's going to give an example. The random forests are a way to go through this search phase. But how we think about this, could I have a new page, please? Oh, that's lost forever. Oh, it's not, great.
Recording.
Ah, awesome. Okay, so what we've got is, imagine that, let's just summarize that table I had. So there was the, do I play golf, yes or no? And let's say that I had looked over a bunch of occasions, and there were 13 occasions on which I played golf, and there were 7 occasions on which I didn't play golf. Now what we want to do is to find a tree that at least gives us a better answer than that. So if I ask my first question, so let's just represent that as number 13 followed by the number 7, and I ask the first question, which might be, is it raining? If it is raining, and I end up with, let's say, 8 cases in which I do play golf and 2 in which I don't, and then I would have 5 cases in which I do play golf and 5 cases in which I don't. Well, my choice over here is 50-50, which is not so great, but my choice over here is 8-2, so this is a much more valuable state to be in now. And so we can see, like intuitively, we can see that we're at least making progress on this branch towards answering the question. Now, what's the exciting maths that's all going to get us very, very hot under the collar that tells us that this is indeed what's happened? It's a thing called Shannon entropy, which is basically an encoding of the amount of information in a fact. There is absolutely zero information in a 50-50 choice. So if I were to say, I have decided that I am not going to play golf on the basis of a 50-50 choice, that is basically the worst I can do. If I had a situation where I had actually 10 yes and 0 no over here, then I would have like 100% information. If I decided yes, I'm going to play golf, then I would be correct. There would be absolutely no loss in going from 100% knowledge to a decision. So the entropy, intuitively, we see that the entropy of this information, of this decision, is much greater than 0 and a bit less than 1. And what like a particular algorithm for designing a tree is to locally find the one question you can ask that gives you the most information gain, and then do the partitioning, and then come up with the next question that gives you the most information gain. Now that is not guaranteed to give you a tree that actually exactly solves your problem. So what you get is a what's called a confusion matrix, which is a great thing, particularly lasting on a Friday afternoon where we've all given up thinking for the weekend. So this is whether the fact, this is the fact of whether I play golf or not, and this is the decision tree's guess of whether I play golf or not. So let's say that what we have is, that 7 goes down there now because that is let's imagine that I had the perfect tree. I have, every time the answer is actually yes, the tree says yes. Every time the answer is actually no, the tree says no.
Can you label the left-hand side? The yes and no?
Oh, yeah.
Yeah.
That would be absolutely perfect. What we're likely to get is something like that, which is not particularly accurate. And what we can see is that most of the time when this tree says yes, I do want to play golf, it's actually right. But most of the time when it says no, I don't, well actually like roughly half the time when it says no, that's not necessarily right. So we might decide to use that tree and to like just toss a coin if it says no, but if it says yes, then we're probably good to go. Or we might decide to build a tree with a different algorithm, or to select a different one from the forest or whatever. This golf example is actually a training set from an example online, and what I discovered was that there was a case where let's go with this, where there's the truth is there are 13 yeses and 7 nos. What it would do is one algorithm created a confusion matrix where there were 13 yeses, but they were here, and there were 7 no's, but they were here. And this means that the tree has kind of inferred some information where it doesn't exist. If I had a tree where the answer was yes, I would have done just as well out of this tree as out of whatever one it was that this algorithm came up with. So that means that there's no information gain. And so that's why you have to be quite careful at interpreting what a decision tree is telling you. Like the fact that you have these questions are asked in this order. So maybe it asks question C first, then question A, and so on, doesn't necessarily tell you anything real about the properties. If like the weight, if the information gain in the questions at this level is roughly equivalent, you could have equally come up with a tree that asked those questions in a different order. Similarly, maybe what's going on here is that I always play golf on a Sunday, and these measures were taken on a Sunday, and these measures were taken on a Friday, but I didn't capture that information. So it could be deriving like kind of false correlations. And they can also overfit. If you have completely irrelevant information, let's say that I had the outlook, the humidity, the temperature, and whether a coin toss came up heads, and then looked at that, a tree algorithm would be able to fit some kind of meaning to that coin toss. So there's still some expertise goes in, but the main advantage of using the decision tree approach is that the decisions are defensible. Like you can see, we have come up with this conclusion because here is a bunch of questions that we ask. Here is how the data lead us to this conclusion, which is a lot harder to intuit from like a neural network or from some other kind of solving algorithms. Are we good?
Right.
Isn't
questions?
flashing? Is that because it's on?
Because it's on. Yeah, that's fine.
Any questions before I hand over to my learned colleague?
I've got questions about how do you, what process do you go through to generate the tree? But is that the kind of thing that we're going to look at in the random forest talk?
No, I mean that was the kind of process that was talked about there effectively. You basically, I think it would have been clear if you would have just said, okay, how do you decide what the first node to split is? And you basically look at these, you look at the entropy, the information gain for every single feature in your feature set. And that effectively, the information gain is effectively how good your split is, how good, you see that confusion matrix, how unconfused the matrix is after the split for each node.
There's a really simple way of visualizing this. So if you start, you're here, you start, and you've got your 13 yeses and 7 no's at the top, right? If I say, well, let's choose question A, yeah. If I get, say I get 3 yeses over here, 3 no's, and 2 yeses and 1 no here, right? So what I'm saying is, you ask that question, and then over here you're left with these potential answers and these potential answers. Then it's probably not a very good question. Whereas if I ask question B and I get, 4 yeses here, 1 no, and then a bunch of no's on this side and 1 yes. It's probably quite a good question. You split the data quite nicely.
So you basically, every single point in your tree, right at the beginning you do that, and then at the next stage you do that for all your features. It could even be the same feature you've looked at before. That gets, those recurrence, you can basically say, was the temperature above this temperature, and then down the line you say, is it even above, even higher than that, or below, for example.
Got it.
So you can multiple split on continuous variables in this.
And I kind of glossed over how that's done. Basically what you do is you kind of scan up until you find a value where partitioning on either side of that value gives you at least satisfactory, if not maximum, information gain. And you choose to split at that point.
Cool.
Just to understand, so does that mean that there's like one decision tree which you get at one set of B group, what's that B learns?
That approach, following that approach.
You have to say that again, John, because you broke up. Everyone else.
I understood it. Because what you said was, you're going to get one decision tree. Like, yes, if you do that, you will end up with one decision tree, and it will always be the same one. And so what you then do is you look at kind of pruning by removing questions that are redundant, or tweaking to remove variables that turn out to not add any information, or to kind of confuse the.
You don't need to ask questions on every single variable on the tree, or modern algorithms will do the pruning automatically, and that's the way they do it.
So what's this approach called?
Decision
tree. You can't say it's called the decision tree approach.
Decision tree learning, isn't it? That's what's called the AI textbook.
Alright, so this is 18.4.
18.4.
18.3, yeah.
18.3.
So,
Depends which edition.
What percentage accuracy would you say is like good enough then for one of these?
Well, so that's a domain-specific question. That's not
Right,
kind of decision tree question. So what you can do is on your results, you can perform a kind of chi-squared regression test. So you can come up with, like, the null hypothesis is this tree is nonsense. I could randomly pick an answer and I would do just as well. And you can find out what the it's called the p-value, which is essentially the likelihood that you have got a meaningful answer completely at random. And you can set a threshold for that. And so, commonly in the sciences, a threshold of 5% is used, and that means that there is a 19 out of 20 chance that there's a 1 out of 20 chance that the reason this works is because it bucketed some random data in a way that looks meaningful.
Right.
And you choose where you want to set the threshold. If we decided that, like, giving financial advice on the basis that we're 5% sure it's good advice is okay, then we might pick a low p-value. We might kind of try and improve the discrimination, but it's a domain-specific problem to choose.
Cool, that's great. Thank you.